Definition: the sine and the cosine hyperbolic functions. The function e to the x minus e to the minus x over 2 is called also sine hyperbolic function or sine hyperbolic x. E to the x plus e to the negative x over 2 is called the cosine hyperbolic function or cosine hyperbolic x. The domain of both functions is the set of all real numbers. Here is the graph of the sine hyperbolic x, and here is the graph of the cosine hyperbolic x. We will first check these functions for parity to see if they are odd or even. We will substitute negative x in the first function. We simplify, and we see that we get negative of e to the x minus e to the negative x over 2. It means that we get negative of sine hyperbolic x. We conclude that this function is an odd function. We observe also the graph, and you can see immediately, because of the symmetry with respect to the origin, that this is a graph of an odd function. Now let's do the same with the cosine hyperbolic x. We substitute negative x for x, and what is this? This is exactly cosine hyperbolic of x. We conclude that this function is an even function. When you look at the graph, you can see that this is a graph of an even function. Example: let's express the function f(x) equals sine hyperbolic ln of x in the simplest form. Now we are going to replace x by ln of x. We have to rewrite e to the negative ln x as e to the ln of x to the power of negative 1, because we would like to cancel the e to the ln. And we get x minus x to the power of negative 1, all of that over 2. Which is this. Let's simplify more. Common denominator. And we get x to the power of 2 minus 1 over 2x. Let's compare a little bit hyperbolic and trigonometric functions. Sine of 0 is 0 because e to the 0 equals to e to the negative 0. I would like also to recall that sine of 0 is 0. Cosine hyperbolic 0 is 1 because here we get 1 plus 1 over 2, which is 1. And I would like to recall that cosine of 0 equals 1. The hyperbolic function has a lot of common with the trigonometric functions. For example, both have almost the same Pythagorean identities. Let's evaluate that. Just expand everything. And let's start cancelling. And we get 4 over 4, which is 1. We conclude that cosine hyperbolic to the power of 2x minus sine hyperbolic to the power of 2x equals 1. The hyperbolic functions are similar to the trigonometric functions. Let's recall, the basic trigonometric functions are the cosine and the sine functions. Each point xy on the unit circle x to the power of 2 plus y to the power of 2 equals 1 is defined by the x-coordinate is cosine theta and the y-coordinate is sine theta. Let's look at the picture. You can see the unit circle with the equation of x to the power of 2 plus y to the power of 2 equals 1. And if xy is any point on this unit circle, then its coordinate xy are also cosine theta, sine theta, when theta is the angle that opens from the positive side of the x-axis to the point. The basic hyperbolic functions are the cosine hyperbolic and the sine hyperbolic function. Now each point xy on the hyperbola x to the power of 2 minus y to the power of 2 equals 1 is defined by the x-coordinate is the cosine hyperbolic t and the y-coordinate is the sine hyperbolic t. Here you see the comparison between the hyperbolic and the trigonometric functions. So it's exactly the same principle, but here we are using x to the power of 2 minus y to the power of 2 equals 1, which has hyperbola. And with trigonometric functions, we are using the unit circle x to the power of 2 plus y to the power of 2 equals 1. Let's see now more hyperbolic functions. From those two, we can do exactly as we did with trigonometric functions. Tangent hyperbolic x is sine hyperbolic x over cosine hyperbolic x, and we get e to the x minus e to the negative x over e to the x plus e to the minus x. Exactly the same we can do and get the cotangent x, which is just the reciprocal of tangent hyperbolic x. We can also have the secant hyperbolic x, which is 1 over cosine hyperbolic x. And the same with the cosecant hyperbolic x. As you can see, there is really very strong connection between the hyperbolic functions and the trigonometric functions. The domains of the hyperbolic functions. I would like to recall that e to the power of x is always positive to any real number. It means that e to the x or e to the negative x is always strictly positive. From here, it's pretty obvious that e to the x plus e to the negative x is positive because we are adding up two positive numbers. And that's why the denominators are never zero for the following hyperbolic functions. For the first two, is because e to the x plus e to the negative x is never zero. And for the other two, is because the denominator is 2, which is obviously not 0. And we get that all these functions have a domain which is all real numbers. We have only two hyperbolic functions, which domain which is a little bit problematic. E to the x minus e to the negative x can be 0. We can solve that and find that in this case x equals negative x, which means that x equals 0. And that's why the domain of the function cotangent hyperbolic x and cosecant hyperbolic x is all real number, but x cannot be 0. Let's now inspect the end behavior of the hyperbolic functions, and I would like to recall the following limits. Limit of e to the x when x approaches infinity, and limit of e to the negative x when x approaches negative infinity is infinity, and limit of e to the x when x approaches negative infinity, and limit of e to the negative x when x approaches infinity is 0. We're just going to express the hyperbolic functions now, using the combinations of e to the power of x and negative x to get the limit. This is approaching 0, so we get just infinity. At negative infinity, this one is approaching 0, and we get negative infinity. Let's observe this in the graph. You can see that indeed at infinity the graph goes up forever, and when x approaches negative infinity it just goes down forever. We're still doing the same. Now this one approaches 0 and we get infinity, and at negative infinity we also get infinity because this one approaches to 0 and we get that. If you recall, cosine hyperbolic x is an even function, so we were expecting that the limit at negative infinity and infinity will be exactly the same. For the other leftover hyperbolic functions, we are just going to use this fact that the cosecant hyperbolic x is the reciprocal of the sine hyperbolic x, and we will get 0. And we will do the same for the secant hyperbolic x, and we will get that in infinity and minus infinity, the function approaches to 0. For the tangent hyperbolic x, we will do just using all those little limits, and we will get here 1, and in negative infinity, those two approaches 0, we will get negative 1. At the cotangent hyperbolic x, we will use just the fact that this is the reciprocal of that, so the reciprocal of 1 is 1, and the reciprocal of negative 1 is negative 1. As you can observe, again, in both graphs. Here is a small summary. It's an even function, this two has to be the same. This is the reciprocal of the one above it. This is the reciprocal of the cosine hyperbolic x. And this is reciprocal of the sine hyperbolic x. We get that.